Okay, with these definitions in hand for both Bayesian equilibrium and Bayesian games, let's have a look back at our conflict example to get a more complete picture of what the equilibria look like in that game. So if you recall, we had player 1 being either strong with probability p or weak with probability 1 minus p. Player 1 knows that, player 2 doesn't know that. The first thing we looked at was an equilibrium where player 1 would always fight and player 2 would not. And in order for that to hold together as an equilibrium, player 2 had to be willing to not fight given what player 1's strategies were. So if we look at that, player 1's payoff, if this is what, player 2's payoff, if player 1 is doing this, from fighting, they got minus 2 times p, 1 minus p times 1. If they didn't fight, they would get minus 1 no matter what. So what we end up with in that case is by setting these two things, payoffs equal to each other, we end up with a cutoff of 2/3. If p is bigger than 2/3, then there's a high enough probability of the player 1 being strong, so player 2 doesn't want to fight. And indeed, this holds together as an equilibrium in cases where p is bigger than or equal to 2/3. Okay, well, so that specifies then one equilibrium, pure strategy equilibrium, where player 1 always chooses to fight, player 2 chooses not, and everybody's best responding as long as p is at least 2/3. So what about the other possibility? Well, in terms of pure strategy equilibria, the only other possibility for player 2's strategy is going to be to fight. And if we're thinking about what player 1 is doing, well, player 1, it's always a strictly dominant strategy for them to fight. So no matter what player 2 does, they're always better off fighting. So we know that no matter what equilibrium we specify, it's always going to involve player 1 fighting when strong. So it really, that simplifies our life quite a bit in this game. And basically we just have to worry about what does player 2 do, and then what does player 1 do. And if player 2 was not fighting, then indeed player 1 would want to fight if they're weak. But if player 2 is choosing to fight, so if we think player 2 is fighting, then when player 1 is weak, their better response here is going to be to not fight. So that'll hold together. So for player 1, it will indeed be a best response if player 2 was always fighting, for player 1 to fight if they're strong and not if they're weak. So when would this be a best response for player 2? Well, now if they fight, what are their payoffs? So fighting with probability p, they're in the top matrix. What are they getting here? They're getting a minus 2 because player 1 is fighting when strong. So we've got the p times minus 2 here. And with probability 1 minus p, they're actually facing the weak player. And in that case, they're down here. And so they're getting a payoff of 2. Okay. If they don't fight, what's happening? Well, if they don't fight, then up here, they're facing a fighting strong player. Down here, they're facing a not fighting weak player. So they're getting p times the minus 1 and 1 minus p times the 0. So we've got a situation where, again, we set these two things equal to each other. You can check via the algebra that if you set these two things equal to each other, solve for p, you'll get, again, a cutoff of 2/3. And now if p is less than 2/3, then we're in a situation where it's going to be player 2 will be willing to fight. So we end up with an equilibrium now of player 1 being willing to fight when strong, not when weak, player 2 fighting, and this holds together as an equilibrium if p is less than or equal to 2/3. Okay, so just to summarize then, in terms of the equilibria, we found when p was at least 2/3, actually when p is bigger than 2/3, we end up with an equilibrium where player 1 chooses to always fight, player 2 chooses not to fight. In fact, if you go through, you can check that that's the unique equilibrium in that case, and it's basically most of the argument we went through It shows that that's the only best response. And when P is less than 2/3, you end up with the strong type of player 1 fighting, the weak type not fighting, and player 2 choosing to fight in that case. And when you end up with an exact 2/3, both of these are equilibria, both pure strategy equilibria. You also then end up with a bunch of mixed strategy equilibria. So then whether or not player 1 fights or not, and player 2 fights or not, you can check what actually makes the weak type indifferent. So what probabilities would player 2 have to fight with or not fight with to make the weak type indifferent? What makes player 2 indifferent? So you can check that there's some mixed strategy equilibria in that particular case. But basically, the important thing to take away from this is Bayesian games end up having different analyses. They end up with different conclusions. So we end up here with player 2 not able to tailor their action to exactly what player 1's type is. And so, for instance, the weak type of player 1 in the case where there's a high probability of a strong type ends up benefiting. They can end up fighting and player 2 backs down, even though that wouldn't happen if player 2 were able to know that they were weak. In contrast, when there's a lower probability of player 1 being strong, then we end up with player 2 fighting, even though if they knew when player 1 was strong, they would choose not to fight. So again, they're not able to. And here it's that player 1's strong type actually ends up being worse off in this case due to player 2's uncertainty. So how it changes the structure of the equilibrium depends on the probability structure, but basically incomplete information will change the analysis of the game, the intuitions, the insights that come out, and it's a very important modification of the games, and especially for many applications that we're looking at.